Hello, this is Truth Socrates, and welcome to a portrait of linear algebra. Today's video is about linear transformations on abstract vector spaces. So back in chapter 3, we learned about linear transformations from one Euclidean space to another. So maybe we have T going from R3 to R5, or maybe T goes from R4 to R2. So we saw that these linear transformations have to satisfy two special qualities, and we constructed matrices for these linear transformations. So in this video and the next 3 videos, we are going to see how to generalize this concept for linear transformations on abstract vector spaces. So we will see that there are many examples of linear transformations that we have in algebra and in calculus. And one of our main goals in these 4 videos is to learn techniques from linear algebra that will help us to solve certain kinds of differential equations. Now, I hope that most of you will be taking a class in differential equations after this one, and I hope you remember that there are many things that we learned here that will help you out in that class. All right, so I mentioned that there are 2 properties, special properties of linear transformations that we saw in chapter 3. And of course, we want our new transformations to satisfy those 2 properties as well. So suppose that V under this addition and scalar multiplication and W under this addition and scalar multiplication are 2 vector spaces. Okay, so we don't need to have the same vector addition in the 2 spaces or the same scalar multiplication. They can be 2 completely different vector spaces. So a linear transformation, again written as T from V to W, is a function that assigns a unique member W from capital W to every vector V in capital V. So as usual, we call V the domain and W the codomain of our transformation. We want T to satisfy these 2 conditions. Additivity, T of U plus V, this addition is in the domain V, is T of U plus T of V, and this addition is in the codomain W. The homogeneity property, T of K times V, where this scalar multiplication is in the domain V, must be K times T of V, where this scalar multiplication is in the codomain W. And as usual, we will write T of V equals W, and we will call W the image of V under T. I'm sure you're thinking that those addition and scalar multiplication symbols look really weird and scary. So, as usual, we will just simplify those 2 conditions into more natural notation. So we will have T of V plus W equals T of V plus T of W, and T of K times V is K times T of V. So here are 2 diagrams that we more or less saw in chapter 3, and truth be known, I just changed the labels on these diagrams for chapter 5. So we have V and W, and V plus W making a triangle in the domain. So their images, T of V, T of W, and T of V plus W must also form a triangle in the codomain. Similarly, if you have parallel vectors in the domain, V and K times V, their transformations, T of V and T of K times V, must remain parallel with the same constant of proportionality. So that is the meaning of the homogeneity property. All right, so let's start with these 3 very easy examples. And the first one, you might even call it a trivial transformation. So V and W are 2 vector spaces, we have the zero transformation from V to W. Every vector in V simply transforms into the zero vector in W. Okay, so why is this additive? Well, if you have two vectors V and W, they both go to the zero vector, 0W. So when you add them together, you'll still get the zero vector, 0W. So we get 0W plus 0W equals 0W. And similarly, if you have K times V, whoever that is, it will go to the zero vector. And K times the zero vector is still the zero vector. There's your homogeneity. Two not so trivial transformations. We have the identity operator. So if the domain and codomain are the same, as usual, we will call P an operator. So the identity operator simply outputs the same input. Okay, the image of V is still V. So where will V plus W go? V plus W, okay, which is the identity of V plus the identity of W. Okay, and similarly for the scalar transformation, of course. Speaking of which, if you fix a scalar K, you can create a transformation S sub K, S for scalar, and that'll be an operator. Where will a vector V go? It will just go to K times V. Okay, so S3 will take V to 3 times V. Where will W go? 3 times W. Where will V plus W go? 3 times V plus W. Oh, wait a minute. We have the distributive property. 3 times V plus W is the same as 3 times V plus 3 times W. And those are S3 of V and S3 of W added together. So we have additivity, and of course we also have homogeneity. Okay, how about a little algebra? We will let our domain be the set of all functions defined on some interval I, and W to be simply the set of real numbers, which is a vector space. We will construct the evaluation transformation, also known as the evaluation homomorphism, where E sub A will take a function from Fi and create a real number out of it by simply evaluating that function at the point A. So who is this A? It is some fixed number A in the domain I for our functions. Okay? So I mentioned S3 before. What about E3? Okay. Different letter, different meaning. So E3 of x squared minus 5x plus 2 means that we evaluate this function at x equals 3. So what do we get? 3 squared will be 9, not 0, minus 3 times 5, minus 15, plus 2. Okay, so we get, I believe that is a negative 2. Okay, wait a minute, no, negative 4. There you go, I need more coffee. How about e sub negative 1/2? There's nothing wrong with having a fraction there. Of the function cosine pi x. Okay, so step by step, this is the cosine of pi times x. So negative pi over 2. Okay, pi times negative 1/2 is negative pi over 2. Negative pi over 2, what is the cosine of that? That is equal to 0. Okay, so that is the evaluation of cosine pi x under negative 1/2. Okay, so why is E sub A in general a linear transformation? Okay, so we have to prove additivity and homogeneity. Additivity. input f of x plus g of x into your evaluation transformation. What does that mean? Plug in a into f plus g. Okay, but we know our algebra, we know our notation. That simply means f of a plus g of a. Now, wait a minute, f of a is exactly what we mean by e sub a for f of x, and g of a, similarly, that would mean e sub a of g of x. So we have additive. Homogeneity. What if you take c times f of x and input it into e sub a? It means that you plug in a into f of x, so you get c times f of a. Okay? But this f of a simply means, again back here, e sub a f of x. Okay? So that equation tells us that e sub a of c times f of x is the same as c times e sub a of f of x. And we have homogeneity. Now, more generally, suppose that you create a constant vector, let's call it A, made of A1 through AN. So that's a vector in Rn. And we define E sub vector A this time from the same function space to Rn. Okay? So this time, we don't just plug in one number, we plug in all of these numbers one at a time, and we store their outputs separately into the components of this vector. Okay? So since it is additive and homogeneous for just one number, it is also going to be additive and homogeneous for several numbers. Okay? So the details, of course, are in the book, but you can also try it yourself. Okay, so here's an example where our constant vector is negative 2, 7. Okay, so we will define our evaluation homomorphism not from all functions. Okay, we will just define it for P2, the space of quadratic or linear or constant polynomials. And because we have two numbers here that we're going to plug in, our output will be in P2. Okay, so let's play around. What will happen if we plug into e sub a the polynomial, let's say 3x squared minus 5x plus 4? Okay, so the definition says we must plug in negative 2 and 7 into this polynomial. Okay, so what happens when we plug in negative 2? So we'll get 4 times 3, I believe that's 12, minus 5 times negative 2 is plus 10, and plus 4. Okay, how about P of 7? So that will be 3 times 49, and then we have minus 5 times 7, so minus 35, and plus 4. Okay, so the first one is relatively easy. That's 22 plus 4, or 26. And the second one, 147 minus 35 is 112 plus 4. I believe that is 116. Okay, did I do that right? Let's see. Yeah, thank you very much. We do get 160. Ooh, I still got it. All right, so that is the output for 3x squared minus 5x is 4. We will go back to this example later on in the video. How about some calculus? So, our domain will be C1 of I. And remember, in a recent video, This is the space of all differentiable functions defined on the open interval I, whose derivatives are also continuous. Okay, so I mentioned at that time, there's a very good reason why we will require the derivatives to also be continuous. Because our codomain will be the space of all continuous functions with the same domain I. So the derivative, which we will call the differentiation linear transformation, represented by the capital letter D for derivative, will simply take as its input a function and output the derivative of that function, which we usually call f prime of x. Okay? So here is why it's important that the derivative is continuous, so that this linear transformation will be well defined. The domain will be C1 of I. The codomain will be continuous functions, C of I. Okay, fortunately, all of these functions that we're looking at, they're all in C infinity. You can take as many derivatives as you want for these functions. They're all continuous, they're all differentiable. Everybody knows the power rule. Derivative of x to the 5 is 5x to the power 4. Okay, everybody knows the chain rule. What is the derivative of cosine? It is negative sine. So we'll get negative sine of 3x, but we have the chain rule, and we will need an extra 3 for that derivative. Okay, similarly, what is the derivative of e to the negative 5x? Everyone knows the derivative of e to the u. It is just e to the u, so we can just copy this. But again, by the chain rule, we should have a negative 5 in front. All right, well, additivity and homogeneity follow very naturally from two famous properties for the derivative. What is the formula for the derivative of f of x plus g of x? Well, I hope you remember. Come on. It's the derivative of f plus the derivative of g. So you can think of that as d of f plus d of g. That's your additivity. Similarly, what if we have a scalar multiple, c times f of x? What is its derivative? So the c just goes out, and you take the derivative of f of x. Wait a minute, that's d of f of x multiplied by c. There's your homogeneity. Okay, now we mentioned that our domain, let's scroll back up. Our domain is all functions with a continuous first derivative. Codomain is all continuous functions. Okay, but we saw that the derivative of x to the 5th is 5x to the 4th. The degree just goes down by 1. Okay, so we can also say that we can think of d as a transformation from p3 to p2. Okay, because if you start with x cubed, you'll get 3x squared. In general, a polynomial of degree 3 becomes a polynomial of degree 2 when you take its derivative. Okay, and more generally, the degree goes down by 1. So we can think of the derivative operator transformation, I should say, as going from Pn to Pn minus 1. So we have derivatives. What about integrals? Let's do the definite integral. Okay, so in calculus, we learned that if you have a continuous function, so it is from c of I, where this time I will be a closed interval. Okay, then we can take its definite integral from a to b of f of x dx. So calculus tells us that that integral, which is a number, actually exists. So we can think of def for definite integral as a linear transformation from ci to r. Okay, so for example, if our interval were from 0 to pi over 2, what would be the def of cosine x. Okay, so the formula says you take the integral from 0 to pi over 2 of our function, which is cosine of x. So I'll just copy that over here. Okay, so let me refresh the screen. There we go. Now it looks better. Okay, so what is the antiderivative for cosine? Everybody knows it should be sine of x. Okay, but we evaluate it from 0 to pi over 2. So that is sine of pi over 2 minus sine of 0. Everybody knows that sine of pi over 2 is 1, sine of 0 is 0, so we get 1. Okay, so why is this a linear transformation? So again, famous properties this time of the definite integral. Everybody should know that the definite integral from a to b of a sum f plus g is simply the integral, definite integral of f plus the definite integral of g. Okay? Except of course in calculus, you didn't call this the additivity property. You just called it the formula for the integral of the sum. Okay? So that is def of f of x plus def of g of x. Okay. If you have a scalar multiple of a function and you want to integrate it, everybody knows you can take out the constant. Okay. And what's left, of course, is the integral from a to b, or that is def of f. So as I said in the introduction, we are going to develop and learn techniques in linear algebra that will help us to solve certain kinds of differential equations. So here is the first step, the baby step for those techniques. We're going to create function spaces which are preserved by the derivative. Okay, so the word is preserved, and usually you might think, oh, it doesn't change the space. Okay, not quite. Okay, we saw that you can think of D as a transformation from P3 to P2 because the degree just goes down by 1. But we also saw that P2 is a subspace of P3 because every quadratic polynomial, also you can think of it as its degree is at most 3. So therefore, we can think of the derivative as going from P3 to P3. Okay, so after all, x cubed becomes 3x squared. 3x squared is still in P3. That's the bottom line. Okay, so what we're going to do is, well, polynomials, they're nice, but they're not very sophisticated. Okay, so what happens if you look at x squared e to the minus 3x instead? Okay, that's a lot more sophisticated. All right. What is the derivative of this? So we all know the product rule, right? So let's do it this way. I will start with x squared, but if I start with x squared, then I must have times negative 3 e to the negative 3x, right? So what goes with that? Now we have 2x. Let me put parentheses. Okay, times, under the product rule, e to the minus 3x. Okay, so of course that simplifies into negative 3 x squared e to the minus 3x and plus 2x e to the minus 3x. Okay, now where are we going with this? Well, we started with x squared e to the minus 3x, and if I have this function in my function space, then by closure, I also have negative 3 times that function. But do I have this other function? Maybe, maybe not. Okay, so what we're going to do is we're going to include this second function in our function space. Okay, in other words, if I want the space to be preserved, what I want is that the derivative of every function in that space is also another function in that space. In the same way that x cubed became 3x squared, 3x squared is also in that space. Okay, so therefore, I need to investigate the derivative of x e to the minus 3x. Okay, so again, product rule. If I start with x, I must have minus 3 e to the minus 3x. So I will just get this time minus 3x e to the minus 3x. I can erase the square there. But the second half of the product rule says that I have to add 1 times e to the minus 3x. Okay? Well, I think we can just do that. Okay, so what now? If you start with x e to the minus 3x, you get minus 3x e to the minus 3x. And again, if this is already in your function space, you also have negative 3 times that function. Do we have this other function? Probably not. Okay, so now we need to investigate the derivative of e to the minus 3x, and we've been doing that. The answer is just negative 3 e to the minus 3x. Okay, so this is good because now we can stop. If you already have e to the minus 3x, then you already have negative 3 times e to the minus 3x. All right, so now we are going to collect these 3 functions and put them into a basket. Okay, ooh, B for basket. No, B of course stands for basis. Okay, so we will put together x squared e to the minus 3x, x e to the minus 3x, and just e to the minus 3x into a set of functions B, and we will create the vector space W equals the span of B. Okay, so all linear combinations of these 3 functions, right? These calculations tell us that the derivative of any function in the span is still a function in that span. Okay, so that allows us now to say that this W is preserved by the derivative, which we symbolize with capital V. Okay, so to be more specific, if you have this linear combination from B rather, what would be its derivative? Okay, well, linearity says I must take C1 times this derivative, C2 times this derivative, and C3 times this derivative. Okay, so what do? We distribute. Okay, so we have for x squared e to the minus 3x, this is the derivative. So we will erase that and replace with this inside parentheses. This is the derivative of the second term. So we erase that and we put that inside parentheses. Luckily for the last one, it is simply this. Okay, so is that really a linear combination of the 3 vectors? Okay, so let's copy this. And now I want to know, what would be the correct coefficients of these 3 functions when we simplify that derivative in the previous line? There you go. So where will we get x squared e to the minus 3x? There's only one source over here. So we get minus 3c1. So far, so good. Where will we find x e to the minus 3x? Ooh, here's one. So we get 2c1. And here's another one. Minus 3c2. Okay. Finally, where will we get this term? Not here, but there's one over here. So that gives us a c2. And there's one over here, so that is a minus 3c2. All right, so that looks like a linear combination of the functions in B. Okay, now before we move on, I did say that B stands for basis. Okay, so definitely, because we have the spanning property here, we're good for that. But what about the independence property? Okay, so not so fast. Let's review that. Maybe you did this in your homework, maybe not. So let's test these functions. C1 times x squared e to the minus 3x plus C2 times x e to the minus 3x plus C3 e to the minus 3x. That linear combination must be 0 for all real numbers. Okay, let's make the domain all real numbers. Let's go all out. Okay, no matter which x you input, you have to get the number 0. Okay, but let's see. What do all of those terms have in common? They all have that e to the minus 3x, don't they? Let's factor it out. Okay, so what do you get? You get c1x squared plus c2x. Just the c2x, please. And plus c3. So that is equal to 0 times. Whoops. Cut and paste fail. That's better. Okay. So, well, e to the minus 3x is number 0. So we can divide it out. And since the right side is always 0, we simply get that this is equal to the 0 function. Ooh, but when is a polynomial equal to the 0 function? We had a theorem, and it said that thus all 3 coefficients have to be 0. Okay, so that tells us that this B really is the basis for W equals the span. It's an independent set, it spans W, it's a basis. Okay, and we have succeeded in showing that D becomes not just a transformation, but now an operator from W, this span, back to W. Okay, but of course, the original linear combination and the final linear combination, which is here, are not the same linear combination. It changes the function. Now, our computations also showed us that this space W, it is the smallest function space, which contains that original function, x squared e to the minus 3x, which is preserved by the derivative. Okay, so what that means is if you have another function space, let's call it u, and it is also preserved by the derivative. In other words, the derivative of every function in u is still inside u, and this u contains x squared e to the minus 3x. Then u contains the entire span of our 3 functions b, x squared e to the minus 3x, x e to the minus 3x, and e to the minus 3x. Okay, so this makes W the smallest space that we can work with, that we have to work with, if we want to find a solution to a differential equation involving x squared e to the minus 3x. Okay, so of course, by the end of our 4 videos, we are going to wrap it all up with a gorgeous example of solving a differential equation involving x squared e to the minus 3x. Okay, exciting. Right, so our next job is to define arithmetic operations on linear transformations. Okay, so these should look familiar, don't they? Okay, we did that in chapter 3. If T1 and T2 both have V as their domain and W as their codomain, and K is any scalar, then we can define the sum, difference, and scalar product of these transformations. Okay, so what do they mean? Well, we already know what it means, don't we? Okay, what is T1 plus T2 evaluated at V? We just take T1 of V and T2 of V. Those are now in W. Okay, so you add them together under the addition of W. Okay, but as usual, we can just write this as plus. Okay, if you know what addition is referring to. Right? Similarly for minus, this will be the additive inverse of T2 of V added to T1 of V. And similarly for the scalar product, you just take T1 of V, scalar, multiply using the times in W. All right, so here's another example of a function space which is preserved by the derivative. Okay, we have V is the span of sine of x and cosine x. Now, of course, these two functions are linearly independent. We have two functions, they're not parallel. Sine of x is not a multiple of cosine of x. Okay, so that is a two-dimensional function space. So what are we going to do? We're going to have as our linear transformation input f of x, output twice the derivative minus 5 times the function. Okay, now that we are in chapter 5, we need to make sure that our transformations are what are called well-defined. Okay, in other words, we really are staying inside V when we apply these operations on a function in V. Okay, well, let's think about it. We're getting a derivative. Okay, derivative of sine is cosine. We're inside. Derivative of cosine is negative sine. But that negative is simply a multiple of sine of x. Okay, so it's still like a linear combination. Okay, all right. So, for example, what is t of the linear combination? Let's make a linear combination. Okay, how about 7 sine of x minus 4 times cosine of x? Okay, so according to this definition, you take twice of the derivative. So 7 sine becomes 7 cosine, and minus 4 cosine becomes plus 4 sine of x, correct? Minus 5 times the original function. So don't do anything. Just copy the original function. Okay. So do we still get a linear combination of sine and cosine? We better. How many sines do we get? 4 times 2 is 8, and minus 5 times 7, minus 35. 8 minus 35 is negative 27. Correct? Okay. How many cosines do we have? 14 over here, plus 20 over here. So that looks like plus 34. Okay, so there we go. Are we correct? Let's see. Yep, minus 27 plus 30. They just put it backwards. Okay. Actually, that was us. Okay. This was make. Okay. We have the same answer, of course. What does this have to do with adding or scalar multiples of linear transformations? Well, we're just talking about the derivative, right? So it means that p can be written as twice the derivative minus 5 f of x. Don't change f of x. Ooh. Who's the transformation or operator that doesn't change the input? The output and the input are exactly the same. There's a name for that, right? It's the identity. Ooh. I sub v in this case, where this is our v. Okay, so this linear transformation is a linear combination of the derivative and the identity. Take a scalar multiple of the derivative, a scalar multiple of the identity, subtract the second. Okay, for our last topic, and forgive me, I forgot to list it out in our objectives at the beginning of the video, but we're going to introduce the kernel and the range of a linear transformation. Okay, again, the definition is very similar to what we saw in chapters 3. Suppose that t from v to w is a linear transformation. The kernel of t is the set of vectors v from the domain, capital V, such that t of v is the zero vector in the codomain w. Okay? Kernel of t is a subspace of the domain of v. Oh, you know what? That just reminds me. The subspace always has to contain the zero vector, right? So is it true that the zero vector in the domain transforms into the zero vector in the codomain? Yes. Okay. That should remind you of similar exercises in chapter 3. The additivity property will get to this. Okay. So this is an exercise also in chapter 5. Similarly, the range of t is the set of vectors w from the codomain, so that w can be expressed as t of v for some v in the domain, capital V. Okay, so the range of t is now a subspace of the codomain. Okay, so that same equation, 0w equals t of 0v, tells us that the zero vector in the codomain must be a member of the range. Okay, before we show you the picture, in chapter 3, we had another name for the kernel, right? It was the null space of the matrix of T. Have we talked about a matrix for T so far? Yeah, you can rewind the whole, replay the whole video. No, we haven't talked about matrices yet. That's coming really soon, okay? But we can define the kernel and the range without the benefit of matrices. We will find a basis for them using matrices very soon. Okay, so the diagram that we have over here is just like the diagram that we have in chapter 3, where the kernel is all the vectors in the domain that transforms to the zero vector. Okay, so that's your kernel. The range, all the vectors in the codomain, which is the transformation of at least one vector in the domain. Okay, so now we can look at our example. Okay, we introduced this linear transformation a little earlier, and we said that we can think of the evaluation homomorphism, where you plug in -2 and 7 into your function, where the domain is not all functions, but just polynomials. Polynomials of degree at most 2. Okay? And that's important because if it were all functions, we're going to have a really hard time describing the kernel of this transformation. Okay, so let's just focus on quadratics or linear functions or constant functions. Okay, so I want the kernel. Okay, so I want the value for the input to be the zero vector. Okay, so I want this to be both zeros. So that has to be 0, and that has to be 0. And that has to go away. Okay. Yeah, and of course our eventual goal is, can we find a basis for the kernel? All right. Every non-zero subspace has a basis. So if there's at least one non-zero vector, yeah, we probably could. Okay, we want p of -2 to be 0 and p of 7 to be 0. Okay. But do we know something about quadratics? Okay. These two numbers have to be roots for our quadratic. Okay. Can a quadratic have two roots? Yeah, of course it can. But if it has two roots, those two roots, then if you factor that quadratic, think about factoring that quadratic. What should be its factors? To be 0 at -2, x plus 2 has to be a factor. To be 0 at 7, x minus 7 has to be a factor. But is that the only quadratic whose roots are -2 and 7? How about this quadratic? Or that quadratic? Or that quadratic? Right? All of them have -2 and 7 as roots. Okay? So therefore, p of x has to be a multiple of x plus 2 times x minus 7. It can't be anything else. So there you go. We found it. We found the basis for our kernel. It must be a multiple of this. So therefore, that span is the kernel of that isabel for these two inputs. Okay, now what about the range? Okay, the range, for me, the range is usually the harder question. Okay, so the question here is, what vectors, I will call those that vector AB, can be written as, okay, I want AB to be p of -2 and p of 7. Okay, what are all the vectors in R2? Let's call them AB, which can be written as p of -2, comma, p of 7. Okay, so it's kind of like this equation, except now we don't have 0, 0, we have AB. Okay, we are looking for the AB this time. We're trying to solve for A and B. Are there only special values for A and B that will put this on the range? Or anything goes? Okay, all right, so can we find a p of x such that p of -2 equals A and p of 7 equals B? Okay, and of course that p of x, where should it come from? It has to come from P2. Okay, so sometimes, always, okay, what has to happen? All right, so let's think about that a little bit, okay? I'm allowed to pick any quadratic or linear function or constant function. Those are all in P. Okay? Can I find at least one of those suspects? So that when you plug in -2, you will get A, and plug in 7, you will get B. And can I only do that for certain A's and certain B's? Okay, well, I'm only requiring a condition on 2 inputs, -2 and 7. Okay, so we want, here's another way to think of it. We want -2A and 7B to be on the graph of P of X. Okay, so we thought about graphs in the kernel problem, okay, because 0 represents a root, okay. -2 has to be a 0, 7 has to be a root of 0 for the same polynomial. That forced that polynomial to be a multiple of x plus 2 and x times x minus 7. Okay, now what about these two conditions? We want these 2 points to be on the graph, okay? And A and B, maybe they have to be special, maybe not, okay? So here's -2, maybe A is up here. Here's 7, maybe B is down here. Is there a polynomial of degree at most 2 that has these 2 points in the graph? Ooh, I'm not even using GeoGebra, just my fingers. Okay. We can do that all the time. Okay? Because through these 2 points, there's at least one line passing through those 2 points. And lines happen to be proud members of P2. Okay? Since there is a line in P2 passing through -2A and 7B, there are no restrictions on A and B. We can always find a P of X in P2 such that P of -2 is A and P of 7 equals B. So therefore, what does that mean? The range of our transformation must be every vector in the codomain R2. Thus, range P equals all of R2. Alright, there we go. That is our video for today. Thank you very much for joining me. This is Jude Socrates signing off. You'll find me on Facebook as usual, and you'll find the 4th edition on Facebook and at kendallhunt.com. So until our next video, still on linear transformations, I hope you enjoy the rest of it.